Silence. Order. I have returned to the demo scene, to all those people who were so mean. I will destroy everything they got. Make me your leader, vote for evil bot.
Everybody, good morning, and if you're still asleep, please wake up. Welcome to the seminar on KRAFT, BeRo's new physics engine, 3D physics engine. And if you have been to BeRo talks at Revision before, you know that they are stuffed full of technical information, more you ever wanted to know than you ever wanted to know about physics engines this time. Let's start with who we are. The primary culprit in this thing, the author of KRAFT and the mastermind behind all it is BeRo. I'm just acting as his voice and presenting here today. So BeRo is a member of Fabrauch and Zero OK, and you have seen his release yesterday in the 64K compo. And he's also a one-man army and has probably written every piece of code I can ever think of. So one part of that is the physics engine that we're talking about today. So, first of all, what is KRAFT? You probably have heard of 3D physics engines that are being used in computer games or in demos or all kinds of other applications, and KRAFT is one of them. And it's, when we say physics engine, we mean solid body physics. So anything you can throw around in a room. You have rigid objects that are not wobbly, but just as a whole get flung around. What you consider physics in computer games nowadays. They can collide, they can slide on top of each other, and all these kind of things. And KRAFT does these things as a Object Pascal library. So it is developed for use in games and works on basically every operating system that you can manage to get a modern object compiler to run on. So if you have Free Pascal, or if you have Delphi, or if you manage to find any other Pascal compiler, good luck, then you can build it and it should run on that platform. And if it doesn't, contact BeRo, he'll fix it for you. And it's designed on the principles of Box2D, which is an open source 2D physics engine, but it goes further because it also works in 3D, or it primarily works in 3D, and can do similar things as the Rubicon engine of Valve, which is also a 3D engine, and then it basically provides a similar feature set. So many thanks go to Erin Cato and Gregorius for providing all the information, in the case of Box2D, also the source that this KRAFT is inspired by and based on. Okay, so if you are coming here hoping after a stressful night of boozing to learn some simple and gentle introduction into how a physics engine works and how to approach one, you're probably in the wrong talk. This talk is about specifically the KRAFT physics engine and all the gory details of how it is being accelerated and how these things, work in nitty-gritty detail. So if you have never used a physics engine, you may be a bit confused, but still, please stick around. If you have, you may learn something new. So this talk does not fundamentally describe how a physics engine works, but it does talk about how the KRAFT engine does things and why it is awesome. Okay, we start with the overall structure of this physics engine. As you may probably know, a physics engine basically does two things. First, it finds out if I throw something, one object at another, it finds out that they collide, and then once it has found out what collides and what doesn't, it solves the forces and pushes things around and makes sure that things end up in the proper places. And if you just want something that works and don't care about performance, you can do this in a very simple and dumb way, by just comparing everything with everything, you get correct collisions and you get correct forces. It will just be so horribly slow that if you want to push more than 2 apples around in your simulation, you're pretty much out of luck in terms of performance. So we need acceleration. It's all about making things fast and only doing the necessary calculations. So the general structure of KRAFT is we have 3 passes going on to detect which objects are interacting with which other objects. Once those have been found, the integration solver pushes the objects around to fulfill constraints such as they should not poke into each other and they should slide around, these kind of things. And then there's a continuous collision detection phase, which we'll talk about why it is useful and necessary at the end. But let's dive right in. The entire thing uses as underlying parallelization library the PASS-MP, which is also written by BeRo. So it's a multi-threaded object library where you can use a parallel for pattern approach. So you don't just say, I want to divide my space into parallel places, but you basically give a programming pattern to the library, and it efficiently makes sure that the application can run as parallel as possible, which is always useful in physics, because if you have a large number of cores, you can make use of them and can make these things very efficient. So here we've got the diagram. We start with the broad phase of just looking around in a simulation space and trying to find out which objects actually even have a chance of touching each other. Once we've found those, excluded all the others, then it goes into more details, which of them actually overlap and which of those that actually overlap do actually touch. So we start with the broad phase. And the first fundamental approach for looking at which objects are even adjacent to each other in space is to do a boundary volume hierarchy type data structure. Of course, you can, once again, go through your entire list of objects and look pairwise which of them interact, but then you get an n-square scaling, and n-square scaling is always bad if you want performance with large number of objects. So fundamental data structure here is a boundary volume hierarchy type, tree type data structure, inspired by what box2D does. And for every object, it stores an AABB bounding box, basically a rough bounding box around the object. Where does it start, where does it end, in all of the 3 dimensions. And in this first stage, we are only comparing the AABB bounding boxes of the objects in this tree data structure in the vicinity to find out which of the objects are actually close enough that an interaction might be possible. The AABB, of course, it's expanded by a little bit of margin just to make sure that the velocity as things move, even if they're not directly interacting now, they can be very soon, so that is taken into account. And that way we'll find candidates of what objects could possibly lead to a collision. Now, if we do this every time step, this, of course, once again, this works, but if we just do that every time step, it will once again take a relatively large amount of processing power, since we still need to walk through the entire tree and compare all the objects in the vicinity. But we can do better, because if 2 objects have been in contact before, there's a very high probability that they are in contact again. So we can actually skip this test for objects that we know have been in vicinity before. So there's a temporal caching step performed here, where the things that had been in contact before are actually not even considered, because they are already in the list. There's a list of possible contact pairs that is only being generated for the newly incoming ones. And as memory management, as objects bounce around the sphere and they become and stop being collision partners, this is all a list, a queue buffer that would become very dirty and have lots of holes. So the memory management is actually done in a way that it's objects that drop out of this are only marked as dirty and only very seldomly is being cleaned up, so that we do not spend the largest amount of time just allocating, shrinking, and growing buffers, but just having this in memory for performance reasons. And then we have found objects that are close enough to each other to be considered, and can from now on ignore the other ones that are far enough away, and go to the mid-level phase. For now, we've only considered, are the bounding boxes around the objects actually even overlapping, or are they far away? So now the next step is to look in more detail The next phase now works on triangle level for meshes, not going from the bounding box into the actual mesh data structure. Is the microphone working?
Battery.
Oh.
Sign language, man.
Are you on? Is it on?
Ja,
Hello? Yeah, okay. So the second phase then works on triangle level for each of the objects. Now we've got possible contact detection. So now we have to find out, is each individual triangle of one of these meshes actually touching something else? But we're not yet looking at triangle intersections. That would still be very much expensive, but we do this first step by taking all the triangles of one object and just comparing it with the convex shape or the convex outline of the other object. If we have a highly structured, imagine you have a Mandelbulb or something like that object in your scene, and you want to look at every nook and cranny of that, that would be very expensive, but instead you first match a rough convex shape outline of it to see if it matches. And again, there's a new list of contact pairs being created, and the ones that do not intersect with the convex hull are being discarded very early and right away. And once again, this slide is almost identical to the one three before. There's temporal caching being performed because once again we can see if two objects are close together and are touching, they probably have been the time before. So we can temporarily cache this information that they were, and also further on we'll see that we can hold some information in memory about how they touched, because that can speed up our computations later on. And it's a very similar buffer structure. And then, yeah, I guess. Okay. And then we come to the actual final narrow phase of collision detection. Here now is where the actual triangle intersection tests are being performed. So now that we've first discarded everything that's not even close to each other, and we discarded everything that's not even touching our convex hull, finally we have to, fundamentally we have to come to the triangle test at the end. And that is then being done on a mesh by mesh pair basis. And here's where the parallelization really comes into play. All of these grids are parallel, but this one has been designed in a way that there's an individual worker thread that covers, in parallel, these contact pairs, and we make sure that it's sorted in a way that as much speed up as possible is being done in the parallel process. So just to clear things up a bit about convex and concave shell, if we have a collision mesh that looks like this, in the first stage we're just looking at the AABB outline of it. The second phase just looks at the convex hull. So a convex object is one that has no corners going in. And only in the third stage are we actually looking at this large list of triangles. As you can compare these, you will see that looking at an interaction with this one is easier than looking at an interaction with the actual full mesh. So that's the extrapolation step. If you have an arbitrarily shaped mesh consisting of a set of nodes, convex at C, this generation of the convex hull is actually a function that is also automatically done by KRAFT for you, so you don't need to pre-generate the convex hull and store it in addition to your mesh, but it's being done by KRAFT for you, and it stores these in the data structures it needs by itself. Okay, so now we come to the actual process of what happens in this physics step once a collision between two objects has been detected. Let's, for example, use the example of two boxes being stacked on top of each other, which is probably something that happens quite often in computer games. So the upper one comes in, and then what happens is it penetrates into the other object. This is what a collision looks like. And now, of course, if we want to have this as physical as possible, this should not happen or should not be visible as sticking into the surface for a long time. But what we actually want is it comes in, and it either, depending on the material, bounces off or comes to a rest on the surface. So now it's the task of this engine to correct for this displacement into the other object. So the first thing we need to find out is what is our contact point? Where did these two meshes touch? and how far did the one object penetrate to the other. So this data structure simply gives a position and a depth of penetration of one object into the other. But then there's a possibility which occurs quite often. If we just want objects bouncing around from each other, looking at single nodes is probably sufficient. But if we actually want stuff to rest on top of each other stably and without wobbling about, it makes much more sense to find a contact manifold. So in the case of a box, that's just a contact plane, but it can have a weird shape as well. So to find a contact manifold between these two objects, to be able to say, I have a number of points which form a continuous manifold which is in contact with the other one. Especially when it comes to things like friction, you need the surface area of things touching, and this is the data structure that represents this contact manifold. As you can see, it contains a number up to 4 contact points, and then the normal direction that the surface, the touching surface of the two objects has. And so to solve this contact problem, what we now need to find out is in which direction do we have to move this object out to get something that is just touching and no longer penetrating. So in the 2 coordinate systems, this contact point has R1 and R2 as vectors, and then we can calculate a velocity, or well, it's actually a displacement we want to get this object out again, but we display it as or internally it's represented as a velocity in which this has to move to become a part again. And it's simply calculating by taking this vector expression and moving it along the normal. And what will result is a displacement acting on one object in this direction and the other object in the other direction. And both are, well, parallel and anti-parallel to the normal. And then, what we can simply do is use this velocity to move them apart. Since we have a fixed time step delta t in the simulation, or not necessarily fixed, but we have a delta t in our physics simulation, we can then say we take our direction vector and just say 0.1 times divided by delta t times this gives us the velocity at which they are being moved apart. So on average, after 10 time steps, they will have separated again. And then, so this is what happens to single penetration points. But if we want to actually find what is our contact manifold, we have 2 different ways of doing this. The first one is to incrementally build it. So first find one contact point. If you find a second one, logically connect them. Oh, this is a manifold, and then find the next one. And the other one is a one-shot manifold process, where immediately, as soon as an object penetrates more than one point, this has been formulated as a one-shot manifold. These 2 have different approaches and have both have advantages and different disadvantages. So the next couple of slides we're going to show which ones, which the advantages and disadvantages are. KRAFT supports both and can be chosen which one is more suitable. And the default one will be to build them. What was the default one? Was to build them incrementally, right? Ah, no, okay, the one-shot one is the approach. So, so let's look at this incremental approach. We have an object coming in with a corner there, which will touch the underlying object and penetrate into it at that contact point. And as you can see, T0, they're still separated. The first time step, the first contact point is being calculated, as we discussed before, and it gives this one. So this one is then being slowly moved out again, just to keep them apart. And the next time step, it can still move. This edge gets a little bit of force upward, but the next one, since it's not yet the contact point, will still propagate or move downwards a little bit. So the following time step, you get the second contact point discovered. And as you can see, this works. It will give us eventually the contact manifold, but if our object is very thin, you can imagine what happens. What happens is that if it moves faster than its thickness within one time step, we get this problem that it can penetrate through, and then you get the usual physics problems in bad computer games. So stuff clips to the floor and starts wobbling about, and so on. And this is the big problem with the incremental building of manifolds. And what we really want is to get a stable contact manifold as quickly as possible. So just for terminology, if we have one point only, and the object is only considered to be in contact there, it can still move about around all the other directions. Nothing fixes it. It fixes this corner in space. Once we have 2 points connected as a contact manifold, it can still turn along this line. And even if we have 3, it may not be able to tilt this way, but it can still tilt the other way. We only really have a stable contact manifold once we have 4 points in place and as part of it. Yeah, so we've seen it works, and it's really great and simple solution to do it like this, and you don't need to, you only need to find contact points, and if you find that their neighbors are also contact points, you build your contact manifold. But it has its issues in terms of stability. So the other alternative is to one-shot them, to be able to find out, once objects touch, what are the touching features that go into it. So again, terminology, we have the clip polygon and the clip plane of our object touching each other with a normal vector that's based on the, well, in this case, this one is the moving object and this one's the static object, but there's always a one-sided view of one object penetrating into the other, and the normal vector is only always defined as of the target. So you can obviously see that this object now moves into the other one, and immediately the 2 contact points are being discovered and then moved upwards and outwards, forming the properly touching manifolds without it tilting in any unphysical way and without it potentially wobbling about this way. KRAFT has a number of basic shapes that it can operate on and do these calculations for. And the basic ones are shape, this capsule, which is just a cylinder with 2 semi-domes at the end, the convex hull of an arbitrary mesh, and then the arbitrary mesh itself. Of course, as you can see, these increase in complexity, so if you're only dealing with spheres, things will be faster than if you're dealing with meshes or arbitrary shaped meshes all of the time. There's no special treatment of boxes. In the superlighter, in the KRAFT world, a box is simply just the convex hull of a mesh with 8 vertices and 6 faces. There's no need for special treatment. It's efficient enough to be treated just as a convex hull. A triangle is also not a special shape. It's just a mesh with 3 vertices and 2 faces. Note, one triangle has 2 faces because it has a normal upwards and a normal downwards. Collisions can appear in both directions. There's no special cylinder or cone shape. If you really want them, you can either also build them as convex hulls, or for many applications, actually, this capsule shape is just as efficient and provides and faster and good enough for whatever you want to do. There's also no real compound shapes. In other physics engines, you may have them, but since you are trying to build a physical world anyway, why not use your physics engine to build your compound shape as something like joint constraints? Things are connected because they actually are connected. There's no artificial way of connecting things in compound shapes. If you really want them, build them physically. Now, collisions can basically be done by all of them with all of them. The only thing that's not happening, that's not possible directly, is to use an arbitrary mesh and collide it with an arbitrary mesh. If you really want to do that, you may want to reconsider if you are not maybe using this engine wrong, because you can always calculate the convex hull for this mesh and collide with that directly. The efficiency loss of colliding arbitrary meshes with arbitrary meshes is so high that for any useful use of this physics engine, you'll want to approximate them either by a sphere or capsule shape or calculate the convex hull. And I guess, yeah, BeRo just tells me, good, thanks for the reminder, it's now actually a good idea to actually show you what it looks like after we've had this dry theory for so long. Because there's a sandbox that we can show. So this is just a UI where the different number of objects are being moved around. Here we've got, here we've got a number of objects in this playground scene. You can see something nicely bouncing down the stairs back there. And it visualizes for us the contact points, so the yellow ones are the contact points, and it visualizes contact manifolds as it detects them. And objects can be pushed around. There's basically, you attach a rubber band to the cursor and kind of throw stuff around in the world. And here we've got a number of test examples. I mean, a box is just a mesh. Here we've got a a very complex shape. This is actually a number of capsules and spheres connected by bone and joint constraints. Here we've got a number of spheres that are interconnected. You can also see these contact points lighting up as these spheres that are connected by these, basically by springs, to also touch each other. And red objects have been detected as stably standing on the surface, so they are not actively being updated, while this ragdoll object is still wiggling about a little bit. Okay, now BeRo is going to activate the AABB tree to visualize what are the bounding shapes of objects, so which ones are considered for collision. And as you can see, there is the boundary hierarchy of these objects means that very seldomly do more than, do they need to look at more than one in the neighborhood. Can you look at the chain of these beads again that are hanging next to each other? You have this sphere chain that you threw a ball against earlier. Yeah, here you can see that this forms something like a stable bridge, and most of the time these objects don't need to consider anything but their direct neighbor. It's very efficiently implemented this way. Yeah. So. That what works. If you have a complex mesh, if you really want to do collisions in, say, a character mesh, you should always consider building it of capsules. It gives a very, very close approximation to the actual shape, and it's much more efficient. Okay. So now we go into details of how these algorithms work and what these abbreviations mean. What we always want to find out for an object when we're checking for collision is what is its support, what is the area of space that it actually covers. So in the example of a sphere, you have the support is exactly the sphere, and in the example of a heptagon, the support is actually defined by these points and a direction. So if you want to collide with something up there, the support for this object at the given time is given by this surface. What KRAFT actually does is calculate this support from the corners, which is a little bit off, but more efficient in terms of data structures here, and as we see, the more common approach, and just good enough for what we're doing here. So here's examples of what these functions look like. I mean, for a sphere, it's obviously easy. If you've done ray marching demos, you'll know that distance function for a sphere, this is basically the same thing. You look at, for a given point that's a candidate for collision, you just look at am I inside the radius. So that's very easy. It gets more complicated if you have the capsule, but this is also still very similar to what a sphere tracing distance function would look like. You look in the direction, decide that you are either part of the cylinder or of the end cap, and then you see if you're inside or not inside of this object. Yeah, this is for a box. Of course, in the local coordinate system of a box, you just check along your 3 local axes if you are in or if you're not in. And it gets more complicated. Okay, the triangle here, we've got, again, the example of 2 faces of a triangle. It can either be up or down direction for your distance. And here's where it starts to get interesting when you're looking at the convex hull of an object, because you have a number of vertices in this convex hull, and you iterate over them to find out whether the direction that you're looking at is intersecting or is not intersecting into it. And now, when you're now looking at collisions, there's an operation that occurs very often that's called the Minkowski sum, or Minkowski sum, depending on your pronunciation. That's actually, if you've never heard of that, but are an audio person, that's very similar to what a convolution does in terms of audio. If you have one object and another object, and you calculate the Minkowski sum, you basically take every vertex or every point of the one object and put one copy of these on it, and get a resulting bloated object that has this large blown up size, which is mathematically it's just a set operation where you put the one object in every point of the other object. And then you can also do the same thing with the reflected object B, which is then sometimes called the Minkowski difference, where the reflected object about the origin is forming this Minkowski sum with the original object. And that is an interesting operation because it creates the so-called configuration space object together. The configuration space object has the interesting property that if it contains the origin point of the coordinate system, then these two objects are touching. If we go back 2 slides to this illustration of the Minkowski sum, if we've got an object somewhere in space here and the other one, and we reflect this one by the origin and then form this Minkowski sum, and the result has the 0 point of the coordinate system in it, then we know these two shapes are overlapping. And that's a mathematically very efficient way of checking for collision. Now, if we want to, we can actually take our formalized hull object of our meshes and actually create this Minkowski sum object, this CSO, this configuration space object of both of them. But once again, that is something that it forms the correct result in this computation very inefficient, because again you need to go through every point and attach each other point to it. Instead, there are now a number of algorithms that give you the information of whether a collision is happening or not without needing to explicitly create this Minkowski sum. And the first one is the Gilbert-Johnson-Kearthy, or however it is pronounced, method of finding objects that finding the closest distance between two objects that are not currently intersecting. So this is implemented in GRAPH, and is the primary way of finding these intersections in the case of this single of the incremental contact manifold process in KRAFT. And it relies on this support mapping function that we just described before, where we look at in a given direction, what is the distance between these two objects, or what is the support in this direction? So it's operating on simplices. Simplex is simply for a given n-dimensional space, this geometrically simplest object of that space. So in a 0-dimensional space, which is a point, of course the simplex is a point. In 1-dimensional space, a simplex is a line segment. In 2-dimensional space, a simplex is a triangle. 3-dimensional space, it's a trigonal pyramid, and so on. If you ever need to write a physics engine in 4D, you have a serious problem. But it still exists there, and formally it's the same kind of process. And the algorithm goes, it starts with a subset. So you take from your large sum d plus 1. So for 3 dimensions, you take 4 points. For 2 dimensions here, you take 3 points randomly, select them. And look at the triangle that they form, and if it and what is the closest point to our collision reference. So you take 3 random points of your convex hull and look at where is the closest point to this triangle, which is easily done either by a numerical calculation, or if it's just a 2D triangle, you can just find the analytic intersection here. And then next step is that you reduce it to the smallest number so that the point is still in this simplex. So in the case of 2D, it's really easy. You just find the edge of the triangle. In a 3D case, you have your tetrahedron, and you find the surface of that. And you reduce it so that you either find an edge or a plane where this contact point is. And the next step is that you move outside of, in the direction of your collision thing until you are again on the boundary of your collision layer. Since this thing is convex, you will only intersect the boundary once, and you assume that this is the closest point. And there we have it. And that gives you the closest point on this boundary without needing to construct it. And now, of course, the question is, how do you solve this? How do you find the closest point on your randomly chosen, what was it called, subset of your convex hull? And one is to solve algebraically. The original paper, it's from an era where computers were expensive and computational methods were expensive, so it was cheaper to actually have somebody sit down and for every sort of simplex calculate the formula that gives you the point. Nowadays it's of course easier to, since it's just a linear equation that's being solved, we use the closest edge to point, closest edge to triangle, closest edge to tetrahedron formula and calculate it numerically. And yeah, the last slide contains all the reference to the original papers and implementation tips for modern versions of this, if you're really into that. Then the other thing is, if you've got two objects touching, this method obviously poses a different problem. Since now you want to find out not just what is the distance to, for example, this object center here, but what is the point where they are overlapping, and where is how is the penetration depth because of these two objects. And there's the method that KRAFT uses here is the Minkowski portal refinement technique. And that was published in 2006 and is also used in quite a number of computer games nowadays. It seems to be the gold standard method to find the contact points. And it similarly works on this support mapping function to find the correct answer. But it does not give a shortest distance, but it gives the contact point and the penetration depth. And yeah. So the way that it works, and I'm not going to read all this text here, the way that it works is actually kind of similar to how a Doom engine finds the way or path finding for enemies to a level, because you've got your mesh as you've got your boundaries here, and you basically calculate the portal. This is why it's called Minkowski portal through these different surfaces. So from your initially chosen triangle, you look at how will your ray be transformed out until you reach the surface, and the details are unfortunately more complex than can be explained in this talk given our limited amount of time. But A, we've got the entire description on the slides, and B, if you're really into it, the references at the end give you an idea of it. But if you've ever written a Doom-like ray margin engine, this is very similar to how it works. And it has the advantage that it does not only just work in 2D, but also in higher dimensions. So if you've got a 2D thing, this portal you're trying to reach is a line. In 3D, it's a triangle. In 4D, it's a tetrahedron, and so on. And then, now that we've got the collision point and we've got the penetration test, we need to find a quick way to find out if objects are still touching or if they're separated. So there's this so-called separation axis theorem, or it's actually not a theorem, some people call it that, but it's just a method to quickly test if objects are touching. The easiest way, instead of just comparing all the points pairwise with one another, is if we can find an axis of minimum penetration, and if we can lay a plane between two objects, the object obviously not touching, and if we find the axis perpendicular to that plane, that's the axis of minimum penetration, and we can then look at support on this axis to see if they touch. And I think there's an image coming up about that. The result of this test will then be stored from the last frame in one of these acceleration data structures, so that if objects were touching before or were just not touching before, there's a very high chance that this could still be the case in the following one. So if we do detect it last frame that objects were touching, we did detect it again, we can use the information here that to accelerate our collision in the next one. So this is what it looks like if we have two objects and they are just separated by this plane. This is our minimum, the axis of minimum penetration. What we look at are the intervals on this axis. If this object and that object map to completely separate domains on that axis, of course they're not separating. And if they are, we can actually store by which degree they do. So that is example code without a Gauss map to calculate this overlap or to calculate this axis projection. It's simply really just choose the axis projected onto it. Yeah, and here then we can find the best penetration phase. So we find the phase, if we know they are penetrating along this axis, we can find the best penetrating phase of our complex hull simply by looking at the normal direction of it. By looking at which is the object that is pointing along this which is the phase whose normal is pointing along the axis most, is the most likely one to have done the collision of these two objects. Yeah, there's reference code from box 2D, and it's this is by the guy Gregorius that was mentioned earlier, that accelerated this whole thing by a Gauss map, which we unfortunately also can't go into much detail about. Okay, once the axis of minimum penetration is found, and we have detected if they are touching or not, this most anti-normal phase on the other side is named the incident phase. Since we are talking about a convex hull here, if there's one phase that's most anti-normal, so if we have our colliding object here, and the phase that is most strongly perpendicular to that direction is used as the reference phase. Since our objects are convex, we cannot have one that's more and then less again and more and less again, but the entire shape allows us to use this optimization. And that one is then clipped against the reference frame, and the resulting points are culled. And that gives us the contact points that we then finally use for our physics update. Here's, this is just the example code that this is the, here you can also say the code aesthetics of KRAFT. So it's a lot of physics code which contains a lot of ugly equations all the time, but that's how physics code tends to look like. So now we've discovered what our objects are, we've discovered if they're touching, and we've discovered what their contact points and penetration depths are. Now we need to go ahead and actually solve for our physics equations. The solver can then take into account contact constraints. So for example, if you have two objects, a box resting on top of each other, the contact constraint is that they will not move through each other and they will not just bounce apart, but they will most likely have a sliding motion like this. That's a contact constraint. And the joint constraint is something like two objects connected by a hinge, as you've seen already in the example. That's inspired by how Box 2D does it, which was based on position-based dynamics paper in 2000 and short time back. It's something like the nonlinear Gauss-Seidel optimization, and I've never heard of a Baumgartner-like parameter correction, but if you've heard of that, it uses this. So the way this physics step is then being performed is we have this penetration into the other object, and it's moving our thing out again. At the same time, gravity is pulling it, and then the constraints are acting on it. So the sliding constraint wants to keep it in the sliding plane. The joints want to keep it in connection, and most of them actually disagree with one another, and it converges slowly to correct, or more or less quickly, to correct physical behavior by iteratively performing each of them after each other. Now, if you really want perfectly correct physics, you would have to have an infinite number of iterations, which of course will not be numerically practical, but these things can be chosen depending on the application, if you rather favor speed or physical correctness. So these can be chosen, and I think they can be altered at runtime all the time. And then, if continuous collision detection is off, we are done here, but we can do a little better than this, because what we've now been doing is a discrete update step. So we take one point in time, we locate where our objects are, we calculate the forces for it, and then we update for the next one and find our collisions again. But that causes a bit of a problem, because if you look at an actual ball bouncing in physical space, you have it moving here with high velocity, and here, for example, it bounces on the surface and you find it correctly. If you have this equal time stepping, it can happen that sometimes this bounce is actually not happening at one of your time step points, and what happens is this, it just clips through. So if we're just looking at physics in equally spaced time steps, or discretely spaced time steps, this is a problem that can commonly occur. However, we can do better with continuous updates. So one solution, of course, for this problem is simply to make walls and floors thicker, so that nothing ever moves more than one wall thickness. But as you can imagine, that's, well, it's not cheating, it's just a very clumsy solution. But solution 2 is you can add speculative contact points to your calculation. You look, after you've done your physics update and you know your new velocities of things, you can look for potential contact points in the future and find or already consider where may this object hit, so that you can add additional constraint to the object. Basically, as you are approaching the surface, you already add something like a spring to make sure you're not clipping through. That's one solution that you can use. Of course, these can cause problems as well. They can cause invalid contact points. If you imagine you have a swing swinging above this surface, and it's moving downwards, and you're considering, oh, I will hit this table, and you add a constraint here, this will alter your motion, where in reality you would just swing over it. So predicting the future, again, is something like solving physics, and of course you want to be faster than doing the actual physics solution, so you'll have to do some approximations here. And of course it makes it more complex once you get more and more constraints to solve. The solution 3 and 4 use the time of impact, which are actually better than that. Instead of predicting forwards and trying to not hit, what you're actually doing is predicting forwards and calculating when you will hit, and then either non-substep the solutions. So you, for example, can say, I have an object hitting this surface. I've updated the last 2 steps, and I know I will hit in the next one. Or I will actually clip through in the next one. So instead, I am already performing my collision here as if I had already hit the surface, which of course will cause this offset to happen. That's the non-substepping solution. Or you know you will hit the object the next step, and what you're actually doing is physics substepping it to the surface and then performing the collision here, which is, again, the correct solution, but takes a lot more CPU time because you need to do multiple steps. So that's a trade-off you have to decide about. If you are only concerned that you do not clip through objects, the one where you reflect up here may already be good enough. But if you, I don't know, if you're simulating table tennis, you may want to make sure that your contact point is actually the correct one, and invest the additional CPU time. Yeah, and for example, the different solutions for the object point. There's different approaches to actually finding this object point. One is, for example, in Tomb Raider Legend, they're using a raycast technique, which has all the typical problems you may know from raycasting, that certain shapes are easy to raycast for, others are not. And as soon as you've got a rotating movement, for example, if again you have a swing and you're using a linear raycasting, you may get problems. The solution 2 is do a linear extrapolation of your actual motion, which again is something like a physics stepping, except without any additional forces. But again, it is a linear thing, and you have problems with rotating movements. Or what you can do is actually brute force the thing and calculate in small steps forward. Takes a lot of CPU time, and it's a trade-off you can once again do. It's basically a root finder for a nonlinear equation, so it comes with all the problems that these have. Yeah, and then solution number 4, conservative advancement. You look at 2 moving shapes, and not just at the point where your physics update occurs, but you actually take their relative motion into account. If you have 2 shapes moving at one point in time, and they would be here in the next point of time, you can assume that in between they will be very close. So you actually adjust your calculations, you adjust your support function, you adjust your GJK algorithm to find out what if they, in between 2 times, that would touch. Of course, yeah, the iterative algorithm, you move in time forward, and if you re-evaluate and re-evaluate and re-evaluate your GJK algorithm, you have lots of calls. It's easier than doing a full collision all the time, but it still is, yeah, once again, a trade-off you have to do. Yeah, here's just how this is being performed. You calculate the distance, and if it is large enough, you just carry on, and if it's not, then you keep iterating and iterating and move your objects by a tiny bit. Yeah, there's a new method that's now also implemented in KRAFT. That's called the bilateral advancement, which is a bit more complicated by using the similar to bilateral blurs, a bilateral approach to things. No time anymore to give details about that. Here's a link about that. It's an iterative, not brute force algorithm, which is also a smart way of solving this. Okay, so now almost up. One more thing, if you do want to make a C++ port of this, since I know not a lot of people like to use Object Pascal, just contact BeRo or via RC, or you know how he looks, you know where he sits, so contact him. And if you want to help with this wipeout style game that we talked about last year, that's still in development, also contact him, and yeah. So yeah, this is how this physics engine works, and now you can download it. The link will be in the next slide, and now we can have a little bit of another demo of this superlighter game, I suppose, which uses this engine for a Wipeout style gameplay. So those of you who were in our last year's seminar and were unhappy that they didn't get to see the advanced rendering engine, you also get to see this now. So this is also an update from last year's talk. So yeah, this game uses the physics engine for all of its calculations. So the entire driving physics is being done this way. And now I guess it's time you need to collide with something. Yeah. So here you can see, if you were just using a dumped collision point algorithm and hitting the wall would basically immediately turn us into a tumble. But instead, since it is finding the contact manifolds when scraping along the wall, what you get is friction instead of being bounced around. And that's the most important part that's being worked here. The data, this is actually using the original Wipeout tracks from the original Wipeout game, and it's just implemented it on top of the new physics engine. Okay, so these are all the links you can look at and may want to do. It's actually missing the link to KRAFT itself, isn't it? Okay, yeah, okay. On the first slide, you find the link itself. All the other information about all these algorithms are at the back. And thank you for your attention, and let's see if we have any questions. Sabi.
Wow, that was some static electricity. Okay, I'm not familiar at all with the physics engine development. So my question might be completely off, but so at the beginning you explained that you have like a finer refinement test, or at first you do like a very broad, like okay, if does this thing have any chance of colliding? Then you have a middle test. And then you have like finally, okay, we're going to check triangle to triangle. I'm a little bit surprised. So, what is really the rationale for the middle part? Because I'm thinking, okay, I understand the rough part. You want to really like prune your tests, but as soon as you're going to have like a volume division algorithm or something like that, like a BVH or anything like that. Is that middle step still useful?
I suppose it is. I mean, if you look at the actual assets in a modern computer game, and characters especially, which are the most interesting thing to do collision for, they are very concave shapes. If I'm a human and my convex shape is just a bunch of points around my body, whereas most of the geometry goes in areas that are actually not that relevant for collision themselves. So I think there's a good improvement still being done, even using this method. Any more comments about that? Yeah, okay. So, of course, if your computer game is spherical cows in a vacuum, then you will not get any big improvements. You can probably leave that step out. But as long as your shapes are interesting and have large amounts of structure, it will still give a good improvement there. I mean, since this triangle-triangle comparison is an n-squared operation, anything that brings down your effective comparison count is an advantage.
Thanks.
Okay. Ah.
Hi. I've worked with ODE physics and bullet physics before, and I've noticed that in some cases, and there are very specific cases, you do benefit a lot from cylinder collision.
Okay.
Simply because in the very few cases where you would need them, like you would want to throw a couple of barrels around or something, if you're going to approximate it by mesh, it won't roll very well.
That's true.
If you're going to approximate it by a capsule, it won't be stable very well. And especially in ODE, we had the problem that cylinder-cylinder collision isn't implemented. And we've tried to work around that for a couple of games that we did. And it is really hard, and you never get what you really want. So I think it would be a nice addition to support cylinder collision in KRAFT.
Well, then I guess get in contact with BeRo and get the physics engine tuned to the things you need. But it's a very good thing to consider then. I hadn't actually thought of barrels, but it's a very good point if you're supposed to have them stand up and roll at the same time.
Yes,
Yeah.
it's a tricky case.
Yeah, for every optimization there's probably a tricky case where it doesn't work. But yeah, thanks for the comment. Okay, I guess we can now go watch the compo or whatever it is that just started. Thank you all for being here, and let's see what we come up next year. Woo!